I'll give a moment for YouTube to get ready. All right, folks. This is 1:30, 1:12, or 1:30, sorry, a little bit later than I had anticipated. We are going to, this is again Saturday, the 7th of October, 2023. We are going to do a paper reading of an interesting paper that came out a couple of months ago, which is called Active Retrieval Augmented Generation. This is a good milestone in our project. We did last week, or at least we intended to do RAG, right? Retrieval Augmented Generation. So in a way, this is the next step to it. Please go ahead.
We can't see you or the board.
You can't see me or the board. Okay. Is it better?
We can see you or the board.
Share your screen.
My screen is shared.
You're sharing it.
And now you're better.
Yeah, but the screen is shared.
Maybe zoom on the screen.
No, I will zoom on when the time comes. It's not yet there.
Screen is shared, so it's fine.
Okay. All right. So all is well. All right. So guys, I'll repeat what I said. Now we'll do the first paper reading. Just to give you a format, we are going to read through 3 papers. Between any 2 paper reading, there will be no more than half an hour break. Have your coffee, come back. We are going to have marathon session. We are going to read 3 important papers. The one that I'm starting out with, and all of these papers are directly relevant to the project you're doing. Right? So if you ask this question, why are we covering these papers? Because you need it in this project. It's literally the next step to your project. Right? Before I continue, just to recap, last week we did RAG. If you remember, we covered the RAG paper. Do you guys remember Retrieval Augmented Generation? Right? What was the main idea in RAG? You could take the best of searching, AI-based search, into a known knowledge base, and also take, which people in this field call non-parametric search and or generation. You can take that content that comes from a document corpus, use AI to search through it, use your sentence transformer, cross encoder, and then sparse searching like BM25 and so forth. And we did all of that. We have all of you have implemented by now. All the teams have, in one form or the other, completed your actual implementation from the ground up of that hybrid search. Would that be a fair statement? We have done that. Right? So we are moving on to, you guys are at different stages of moving on to multimodal search and to RAG, Retrieval Augmented Generation. The point of RAG, some multiple benefits accrue from RAG. One of them is you now, just like in hybrid search, we merge the benefits of sparse and dense approaches, dense vectors, and using BM25 or TF-IDF and these approaches, the more traditional approaches, you bring both together. Why? Because for short phrases, sometimes it turns out that AI semantic search doesn't do well. There isn't enough semantics in the phrase, and keyword search does better. By putting both of them together, retrieving results, and then sieving it through a cross encoder, which tends to be a little bit more expensive, right? Far more expensive actually, and you're sorting through a smaller list. The net benefit is sparse search is lightning fast, vector search is lightning fast, right? But both of them, you're treating them as mechanisms to give you a short list of candidate search results, isn't it? And from the candidate search results, I don't know if you guys are seeing my expressions. So you get a candidate search results. Now comes the question. You're not saying that these are the search results. You're saying, okay, I got 2 candidate lists. When you do such fast operations, what you gain is obviously speed, because if you compare a query against all the billions of documents you have, it will be extremely slow. But you have to take shortcuts. You have to use approximate nearest neighbor approach and this and that. And so you shoot for getting high recall, not high precision. Then precision is low. You don't know which of these documents are more relevant than others. Then you sieve it through a cross encoder to re-rank it, and hopefully in the process gain back some better precision. The more, go ahead, Patrick.
I said, is there a general rule on knowing what's expensive in terms of like, evaluating? You said
Yeah, it's very simple. See, Patrick's question is there a general rule for knowing what is expensive in this? So here is one general rule. Anything that scales as linear at inference time is very expensive, right? So, excuse me, 1 second. So, I apologize. So, see, if I have 1 million documents, and if I have to compare a query against millions of documents to know how similar it is to each of them, then when it becomes 2 million, my latency will double, right? When it becomes 10x the document. So at inference time, you need things that scale sublinearly, right? Like that. And that is what approximate nearest neighbor algorithms give you. Right? That is one. The other thing they give you is cheaper comparisons. See, when you, for example, in a typical BERT, the 2 sequences that you feed in, 2 sentences, you do that, it typically will take you, let's say 100 milliseconds or 200 milliseconds per inference, right? Or 50 milliseconds per inference, whatever, based on the GPU you have, right? But if you compare 2 vectors, a dot product, a cosine distance, it is lightning fast, right? It is like, you wouldn't even take a millisecond. So that brings about its own performance gains. And that was the whole point of doing sentence BERT, like using a contrastive loss. You found a mechanism to just land a vector in the neighborhood of other vectors that mean similar things, semantically similar things. And then vector search is extremely fast. So that's the thing. But then along the way, what you lost is the more derivative things you do, you're not comparing a sentence to other sentence, but you're comparing a derivative object, namely a vector of one sentence of the query to the vector produced from the documents, right? So those are derivative objects. You lose some precision there, some things there, and some information there. And the second thing that you lose is you do approximate nearest neighbor search, because still it is order n search. Because if there are 1 million vectors sitting there, you don't want to do 1 million comparison. The point of ANN is you can do sublinearly, right? You can do logarithmic time or even less time. Right? So that is speed. Now, when you come back and then you say, okay, I have 20 results, I have to produce 10. The question is of re-ranking. You have solved the recall problem in one way of thinking about it. The other problem is you need to make it more precise. You want the most relevant results to bubble to the top. Now is the time to bring out your big guns, things that will take a lot of time. So now you bring in your full, matcher, BERT matcher or any form builder, encoder matcher, cross encoder, because that, even if it takes, let's say it takes, for the sake of argument, 50 milliseconds per comparison, you're comparing the query to only 20 sentences, isn't it? Which means that you'll still have a response in 50 times 20, right? That is in 1 second, which is pretty fast. That is one way of looking at it. Right? Though ideally with good GPUs, etc., it doesn't even take a second. It takes much less than a GPU bank. So that is getting the benefit. So this hybridizing or taking the best of both the worlds is exactly the idea that RAG essentially brings. RAG now says that, see, when you answer a question, there are 2 ways of answering it. You go to an LLM and you say, all right, tell me the answer to this. Now think about an LLM. LLM is a giant transformer, right? What is it made up of? Weights and biases. It's made up of parameters. Right? And somewhere in its vast ocean of weights and biases, these parameters, is a statistical model that that sort of mimics a form of memorization, right? Or effectively can remember and regurgitate, well, not quite regurgitate, but come out with an answer to your question, isn't it? But remember, it is produced. There are multiple aspects to a LLM, and this goes to the heart of it, guys. See, at the LLM, let me take a pen. Suppose you have this, imagine that you have this vast ocean of weights and biases all interconnected. So this is my weird way of writing an LLM, right? And at the end of it, you have a dictionary of English, let's say 30K words. What is happening? At any given moment, it is conditioning on, so the next word that gets produced, probability of a token, the next token, T next, is conditioned on the tokens that have been generated so far, isn't it? And the input, right? This is, in a way, one way of looking at it is a giant conditional, Bayesian conditioning in some sense. Does that make sense? Right? And in some sense, I'm obviously using sort of hand-waving arguments, and it produces a next token. But when it produces the next token, what it means is that this guy, to different extents, these things get lit up. Let me just say, this gets lit up much more, this gets up lit less, this gets up lit really high. What is it saying? Different tokens are getting lit up. If you think of them as bulbs, the formal word, of course, is logit, but I always think of them as bulbs. All those bulbs, the 30,000 bulbs, they get differentially lit up, right? Now what happens? Even when you softmax it, namely make it into probability, now there is a thing. And just to recap, what do we do? When we softmax this, the next stage is softmax this, logits, and a temperature parameter T. What does temperature do? By the way, temperature usually in these LLMs, they give you 0 to 1, right? Or 0 to actually open-ended. You can put whatever temperature you want. When they mean temperature 0, actually in a more mathematical sense, they mean 10 to the power 0. Means they are not scaling the value. What is temperature? You scale each of the values. So suppose this logits here is output 1. Let me just call it theta 1, theta 30K. What you're doing is the temperature just says scale everything by this before you exponentiate it, isn't it? So the temperature 0 is actually temperature 1 because implicit is that you're doing 10 to the power that. Check whether it's 10 to the power or e to the power. I don't know. It's escaping my mind. In case it is e, correct me. So, but in other words, you exponentiate it. At that moment, what happens is there is a dampening effect. So if you raise the temperature too much, then what happens is this thing becomes shorter, right? This gets even shorter. So the relative differences are not so pronounced, right? And then comes sampling. The next stage is you sample off the softmax. When you sample off the softmax, what are you saying? I'm going to flip a coin in such a way. So here is one way to think of sampling that I think of. Whatever these values are, imagine that you have divided a land into patches of that size, right? Rectangular patches, whatever patches of that size. So if some logit is big, or even after temperature scaling, after softmax, and softmax is if something has a high probability, let's say 75% probability, just give it 75% of the land area, right? Make it Texas size or Alaska size or something like that. If it is a small one, then give it a tiny amount of size, maybe what would it be? Main size, right? A little territory. So imagine the whole patch, the whole probability map is a United States map. And each word gets a territory the size of its probability. Then you do one thing, close your eyes, throw a dot, magical dot from a spaceship, right? And throw it towards the United States and see which state it lands. Yeah, it may land on the biggest one, it may not, isn't it? There is still a probability it might land somewhere entirely different. It might even land on the least probable word. You see that? So that is sampling. So that is why the crucial thing that you have to remember in all of these is that you always sample of the softmax. And think of it like that. See, guys, I tend to use sort of, I don't know, it looks weird or corny examples, but to me, it just makes the intuition clear. If you think of probabilities as area on a page, on a land, on a map, and you're throwing darts at it, right? Remember, sampling is throwing darts and asking, where did it land? And wherever it lands, you pick that word. That word is your next word prediction. And remember, LLMs are next word predictors. That's what an LLM is. In effect, that's one way of looking at it. That's how they're designed. That is both its strength and its limitation. Now, why would you want to keep the temperature high? When you keep the temperature very high, what happens? Things get dampened down, flattened down, right? So reminds me of a saying in Hindi. I don't know if how many of you know Hindi, I'll just say it. It goes something like this. Andher Nagri Chaupat Raja, Take se bhaja, take se khaja. Anybody has heard of that? What does that mean?
Anything and nothing.
Yeah, it basically means there was a foolish king in a kingdom, dark kingdom, filled with darkness, where the king had set the price of everything to one rupee. So sweets would go for 1 rupee, very precious things would go for 1 rupee or $1, and trivial things would go for $1, uniform pricing, right? So obviously it's supposed to be not a very wise thing to do, isn't it? So that is exactly what you do. When you raise the temperature too much, you flatten everything down. High probability, low probability, each of the words get an equal real estate on the map, isn't it? So what is the consequence of that? When you sample off that, does the language model have any sense at that moment? Is it even distinguishable from randomly picking whatever? So asymptotically, that is one limit. Now look at the other limit of it. What if you set the temperature to, well, they say 0 in these APIs, but actually it's exponentiation of 0. What is the exponentiation of 0? 1. It means that I'm dividing each of these bulbs' brightnesses, largest, by 1. Means I'm leaving it alone. So the tallest guy, if it is really tall, it's quite likely that your dart will fall there, isn't it? And so it's more likely to be generated. Now, what is the implication of that? Now, tell me, why is this this is a desirable? Because you get a result that you probably expect, right? LLM in action, because the whole Bayesian conditioning is coming through at that moment. Well and fine. Why would you not want this? Why is it that people sample? So let me ask another question that sort of prefaces this. Why do we sample of the softmax? Why don't we just take the next word, the highest probability word? Patrick says we need some variation in the output. Anybody else?
Even though it's a probability, it's still needs to be.
Yeah, Shanava says even though it's a probability, it's still a probability. There is still a probability, there's a chance that it may be wrong. Anybody else? See, there are many answers to it, and one can say it more mathematically, but here's the way I would say it. There are two answers to that. First of all, remember, somewhat like what Shanava said, that in machine learning, there's always a risk of overfitting. And when you just always deterministically pick the highest probability word, right, you realize that it will produce the same answer over and over again, the same query, isn't it? assuming that you have not retrained the model. It's a deterministic model. One good thing with it is it's a deterministic model. If you want repeatable answers, well, throw away something. But you don't do that because these things tend to, you don't know how much overfitting it is and whether what it's producing is the correct thing or not. Right? So sometimes, and also it doesn't leave you possibility for reinforcement learning. Right? All of these LLMs need to go through reinforcement learning. What do? If you sample off it, you generate one word and the next token and the next token. Because there is conditioning on these tokens, what will happen is even slight deviations will lead to entirely different territories. It is literally molecular diffusion, if you understand diffusion of gas molecules, right? Random motion, right? Once you take this trajectory, your next path is a random walk from there onwards, right? It's not exactly random. Random walk assumes that there's a meaning there, but it becomes, so suppose the next, so if you think about it, a probability of t n plus 1 now depends on what you committed to, the token that you accepted, isn't it? So it determines what the next token will be. Are we making sense? Right? And so what happens is that if you think of it as a space of possible trajectories, let's say you can go like this, you could go like this, you could go like this. You see what I mean by that, right? You could have entirely different trajectories. What are those trajectories? Those are sequences of tokens that are coming out, isn't it? And therefore, you're generating entirely different outputs. But why would we want to do that? Because we just paid a heavy price. We lost determinism, isn't it? We just made it into a stochastic machine. Yeah, go ahead.
So I think at this point, we don't know if the LLM is overfitting to that particular token.
We don't know. We don't know. But you should always go with the assumption that with this gazillions of parameters, there is a lot of overfitting. One way to know that it's overfitting is why is it able to regurgitate sometimes entire passages? The reason it's able to see, memorization is another word for overfitting, isn't it? Yeah.
A very basic question. The problem where we did the hybrid search, the hybrid search isn't RAG, right? I mean,
No. It's not right. It's not.
So
We'll come to that.
So now my question is, why isn't hybrid search a research paper itself? Like, because semantic search.
No, it is. If you look at the sentence word paper,
right,
hybrid search is deeply rooted in the very first paper itself.
I see.
It is a section in there. Or that or the follow-up paper, I forget which one, but it is there. So, all right, coming back to this thing, guys. So follow this lead of ideas, because if you want the intuition on this paper correctly, please follow through and pay attention. So you realize that you have a diffusion, you have different trajectories, different sequences coming out. That opens up the possibility of what? Many things.
Unpredictable.
Yeah, unpredictable. So there's stochastics there. Now you have introduced stochasticity. You would say, well, isn't that idiotic? Why would I want that? Why would I want that? Because what it has learned from may not be right. It scraped the web. There's a lot of toxic nonsense there, right? So the most deterministic answer is often sometimes not the right one, because the web has plenty of disinformation, misinformation, errors, this, that. So what do you want to do? You want to feed it through two loops, through, first of all, fine tuning, but that is separate, but more specifically reinforcement learning with human feedback. So to do reinforcement learning with human feedback, what you need to do is you need to produce, let's say, 20 answers, then ship it out to human beings and ask them, rate these answers, which is the best, which is not good, etc., etc. Then have a reinforcement learning cycle there. Do you see it? Right? And that is the point. You cannot bring in, to open the door to reinforcement learning, one easy way is to sample off the softmax and produce a variety of answers. Right? but you pay a price, couple of prices. One thing you lose is determinism, isn't it? And the second thing that you lose in this process is, see, it is called the diffusion of that. John LeCun, in a very nicely he said it. And I still remember going for a walk at about 5:30 in the morning in the dark, and I was listening to his one of his talks. I believe it was with Lex Friedman, and he used the term diffusion of errors. I liked it very much. So physics-like. Right? What it means is, if the probability of the right answer, what should have been, even if your LLM is really well trained, it is 99.9%, 0.999. The probability that 100 words later it's producing a wrong word is how much? Let's work it out, guys. You all have Python. I want somebody to answer. Go open IPython and do this. 0.999 to the power 100. See what it is.
Minuscule.
It's asymptotically zero, right? It tends towards zero. What does it mean? The more long form generation that you do, the more likely it is to start erroring out. You sort of control it through reinforcement learning. You sort of show it special passageways that go along these well-defined paths. There are less landmines here, in a way of speaking, in a metaphorical way of speaking. But inherently, that reinforcement learning won't eliminate the problem. And the residual problem that you have is your hallucination, isn't it? The models hallucinate. So it is, in a way, the top problem with large language models, isn't it? And one reason, when we did this LLM bootcamp, I wanted to bring you guys quickly to the core problem that has to be handled if you build production grade systems, because hallucination may be funny or hilarious when you're just sitting and talking with friends, right? To find that, let's say, Joe Biden was married on the moon or something like that, right? If a LLM says that, but which is patently untrue or something like that. But it is not so funny when lives are at stake or legal matters are at stake, isn't it? So how do we deal with that? We started with search for a reason. Search, of course, we can do hybrid search, very productive, very useful, a lot of utility. But to me, one of the core values that it brought was retrieval augmented generation. Namely, now we could hybridize the hybrid search itself with large language models. We asked this question. If a question is asked, how many ways do we know to answer it? We can just do keyword search. We can do AI search, but those two we already hybridized. But then search we can hybridize with large language model. We can do prompt engineering. We can say, here are the facts. You prepend the facts, right? And then you prepend the life story of Joe Biden, and you say, he went to this college, he did this, whatever you can scrape off with people. And then you ask this question, right? Which university did Joe Biden go to? But do you realize that now the likelihood that the LLM will hallucinate is much, much less, because remember, it is also, obviously, the most obvious thing is it is conditioning on the input. And in the input, you have given it a fact dynamically at inference time, isn't it? So, and this fact that the fact that the LLM can answer this is not because of its weights and biases. Those weights and biases, those parametric response would have been maybe something else, right? But let me finish the argument, guys. But you have used sort of a side channel of information, search, to bring in facts and give it to it. And therefore, it is in the literature called non-parametric approach, right? And so RAG hybridizes two approaches, a non-parametric approach and a parametric approach, and says now, and it is a beautiful, beautiful example of good prompt engineering, isn't it? Properly prompt engineering or instructing is good instructing, right? And you're saying now LLM. So what it does is it materially reduces hallucination, at least for short answers or for very pointed answers. Are we together? But it doesn't quite solve another problem. If you ask it to do a domain summarization, like let's say, explain to me, well, I was just going to say, explain to me quantum chromodynamics, but that would be, I don't know if it can even answer that. But let's take something a bit more. Suppose you say, explain the solar system, describe the solar system, and it's a long form answer. It might, I don't know whether it will or not, but let us say, let us take some liberties with what will actually happen, but hypothetically say that it might make some things up along the way. It might suddenly posit that there is an 11th planet or 10th planet, planet X, or something like that. Or it might entirely get rid of Pluto. The poor Pluto seems to be having a tough time these days. It is voted out of the planetary system and then voted back in. Right? So anyway, it might do that, right, from the weights and biases. But even when will it not produce the right answer, in spite of you giving it facts about astronomy?
Going to be my question, but maybe in the core there's already some information.
Yeah, suppose I pose a question like this. In view of the given astronomy, right, describe the properties of the 10th and 11th planet, or something like that. Now what happens in the body of knowledge, it doesn't seem to find it, right? And somewhere in there may be a fact that says there are only 9 planets known in existence. But for whatever reason, your AI search will not bring up that sentence. I mean, it gets harder and harder. So what you can do, so you see the problem with it. The longer the text you bring, the more you're fighting that problem that you can call the diffusion of errors, isn't it? So the more likely you are to hallucinate for long passages. You are fighting it with drag, yes, but not. And there are other things. For example, as you know, when you feed it too much text, what happens? The context, it gets, attention gets lost in the context. There's a whole paper called Lost in the Middle. Did we do a paper reading on that or not yet? No. Oh, we have to do that. Okay, we'll do that. Lost in the Middle. So poetically said, right? So anyway, so there are shortcomings to all of this. So now there are 2 ways of answering it. One is to wait for a theoretical breakthrough. What can we do besides just having a next prediction engine, next word predictor? Yeah, that will take some time, but a more practical approach that this paper comes up with is this. It says that it latches on to a key observation. Right? What does it do? Whenever, remember, and this is a fact that people tend not to notice, that actually it is not just producing a token Tn, it is producing Tn and its probability, isn't it? LLM is ultimately sampling off a logit, and whatever word it produces, it says, okay, I sampled, I put, but by the way, this word was less probable. I just happened to land upon that. The dart happened to land on that. Right?
Logit is the softmax value.
Softmax value. Right? No, logit was the bulb, actually is the softmax value. Sorry. The softmax value after the temperature scaling, right? Even though that probability, so that we call just the probability. Even though the probability is low, when we threw the dart, oops, it landed in Maine. Right? Tiny bit of territory from the spaceship. And so I picked up the word. And then that word, consequent to that word and all the words that I've produced, here is the next word, and the next word, and the next word. So what this thing latches onto is that, hey, why can we not look at those probabilities and somehow leverage that to go to our other method, which is search, which is search. Right? So what it does is, I know some of you are waiting to ask questions. Give me 1 minute. So what it does is, it observes. So first thing is, some things are very easy to do. It is producing. So now, should I tell you what it does, or should we walk through the paper first? Let's walk through the paper and you'll see it. Right? But by now you must have guessed what will it do. How will we use that probability? The token's probability. How can we possibly use it? Come again?
Create a trigger word for another set.
Yes. Like Patrick said, we can use that low probability and ask, is any word in the sentence that I've generated so far, what you do is you park your sentences in a buffer. So what you have is, okay, let me explain this paper. Let me give you the big picture so that reading the paper becomes easy. This is the LLM, right? It is producing tokens, steady stream of tokens. So what you do is you have this is not what the output is. Output is, so all of this is behind a curtain, right? What you do is you take this token, you can use Spacey, NLTK. These guys use NLTK. I would have used Spacey. Figure out the sentence boundary. Keep track. At any given moment, what they do is they just make a reasonable guess that most sentences are less than 64 words, 64 tokens. Then they look for sentence boundary and they look at the last sentence. Right. Now what they do is that, let's say that the sentence is made up of, the last sentence, T, is made up of the words W1 to WM. Right? M words, M tokens, sorry. I keep using words because token always evokes words, but it could be punctuation, it could be question mark, with words. A token. And I asked myself, what was the probability of each of these tokens? The probability of WM. And I find the min of this. Right? I find which was the weakest word, which was the word on which the LLM was least confident. Now, why would I do that? It's interesting. It's sort of plausible and empirically seen, though I don't know how you would mathematically prove that it is always so. What they have found is, people have found, is that if you observe carefully, before it begins to go wrong or hallucinate, it tends to produce tokens of low probability. Right? It's an empirical observation. So what you do is you set a threshold and you ask this question, is this greater than, equal to a threshold or not? If the minimum probability of a word is below a threshold, if it is above a threshold, now you let this sentence, last sentence, escape into the outside world, right? Push it beyond the curtain. But if it is not, then what you do is you take two approaches. Those are the implementation details, but basically that is the time to, one way or the other, dip into your search, right? And ask this question. What do we know? And whatever we know, what we will do now is we will make that part of the knowledge base. Are we together? And then have the next the continued generation happen, and then the whatever tokens it has produced, because it needs to still condition on the tokens, right? So what happens is that instead of Tn being conditioned on Tn minus 1 all the way to, so what happens is then you erase this. In a way, you go and you erase this. This is your, think of it sort of like a checkpointing. You use that sentence which had low probability as a way to search, but when you got it, you fed in this much. This is your Tn minus 1 to T, this, and the X, the input that you give, which is both the query plus search results. search on what? A query term. And we'll talk about what do you query with. Those are the details we'll talk about in a moment. Right. Patrick.
So as just some clarification, so when they say context window as if in terms of this like autoregressive, does this mean that once it's generating more tokens, the context is also adjusting
Yes,
so that it starts to forget the original?
it does actually. Unfortunately, it does. Beyond a certain context length, right? See, no matter what you do, the more recent always tends to have effect, stronger effect.
So there's really advantage of just minimizing either the context or the length of your prompt.
Yes, you should.
So that
Absolutely.
you get the most out of the LLM.
Yes, yes. So Patrick's question is that when the whole context window becomes huge, either coming from what we have produced so far or what the instruction that we give, the information that we give from search, it is in our interest to keep the whole thing short. Shakespeare said it best. Simplicity and brevity is the soul of wit. Right? Very true here. I mean, I'm being jocular, but the bottom line is the more brief you can be and succinctly you can say things to the LLM, the more likely it is that those attentions, cross attentions are made. That's that. So that is the gist. Are we getting it, guys? That's the gist of this paper. Now, I'll read through this paper. So here, one of the interesting thing is, those of you who are used to parsers and compilers, do you remember look ahead parsers? No. So this is pretty much along the same idea. What you do is, you just stop, you just wait. You don't let the next sentence be the final sentence. You wait and you check, inspect it. If it is below a threshold, you throw it away. You don't throw it away. You generate a query from it that you will use in your search engine, your hybrid search engine, for example, right? Or your vector search engine or whatever. In this paper, actually, they didn't even use a vector search engine. If I'm right, they just used a BM25, which probably means they dipped into Elasticsearch or something, right? But if you were doing it, one easy enhancement could be use your newly grown hybrid search framework to do that. So that's so let's read through this paper a bit carefully. I would like to finish in the next 15-20 minutes.
When you say stop, you just stop the generation at
Yeah.
that point.
Yeah, at that point, you stop the generation.
So keep everything that has been written.
Yeah.
How do you do that in terms of programming?
You keep it behind the curtain.
Yeah,
You keep it in a buffer. You keep inspecting the buffer. And when you have high confidence, then you say, yeah, ship it out.
Yeah. So the APIs give you a way to stop.
Oh, okay.
And you can see what happens is, if you look at OpenAPI or anything, DaVinci and so forth, they use DaVinci. You can ask it to generate X number of tokens. That's why they say 64 tokens, no more than 64. So obviously it will stop at 64. Then you look at the last sentence and you say, will I accept it or do I throw it away? Right. That's that. Yeah, as simple as that.
And then you can zoom from there.
Yeah. Then you make the next API call to get the next set of notes.
Another API.
Yeah, another API. So you're in a perpetual loop of making the calls, right? So let's read this paper. Now it should make a lot of sense. I hope that this will look straightforward now. Despite the remarkable ability of large language models to comprehend and generate language, they have a tendency to hallucinate and create factually inaccurate output. We all agree, right? Augmenting LLMs by retrieving information from external knowledge sources is one promising solution, namely RAG. Most existing retrieval augmented LLMs, right, employ a retrieve and generate setup, which means first comes the retrieve and then generate. First, what do? You take the query, go get some search results, then make that search results part of your instruction. In fact, you prepend it. Even before the query, you put the body of knowledge that you got from your document chunks. In your case project, you would call it those chunks, right? You put those chunks there, 1, 2, 3, 4. And then you ask the question, right? Who is the current king of Timbuktu? Or I don't know, something, whatever it is that you want to ask. Am I making sense? So Timbuktu is not a country; it's a place. I'm being silly. Okay. And obviously they don't have a king. So that's what you do, isn't it, guys? Rag, we studied this week. That's what we do, right? Clarity there. Okay. So this is it. That's all they are saying. Employ a retrieve and generate setup that only retrieves information once based on the input. And the crucial operative word is once. This word only retrieves information once based on the input. This is limiting, however, in more general scenarios involving generation of long texts, right? Where continuously gathering information throughout the generation process is essential. Means you have to, as it produces. So it gives an example. See, think about human beings. How do you find out? How do you write an essay or a paper? You yourself write something, then you research some more and write something, and research some more and write something, isn't it? So why not make the LLMs do the same thing? Yeah. Researching here means dipping into the body of corpus of facts. So,
Sorry to interrupt you, but I think this makes sense in the coding part of like programming.
no, long text.
Because-
Easy. If I ask you to write the history,
In the search, RAG actually makes sense because it looks at the keyword search and the index search. But in the coding, all of the, let's
what
say
do you mean by coding?
basically, all this GitHub has this co-pilot, right?
No, let's not bring that in. Let's keep that separate. We'll come to that later on. So let's keep that
I
separate.
do have one point. I think he's along the same lines on what I was asking. That, when we do RAG, we know it's for short answers.
Hmm.
But given that you're doing it for long form, shouldn't you just do it in a loop? That's common sense in programming.
No, but how would you know when to stop and ask and go search for more? And what will you search for? It is a good idea. Yes, do it in a loop, but it leaves open two fundamental questions.
Basically, you can go infinite. That's
Yeah.
where the threshold comes in.
Yeah.
So no doubt there are some nice things, but I believe when he is referring to programming,
Mhm.
what he is also saying is if you're generating a long form and we know RAG is for short form text.
No, you
right?
don't know that. People have been using RAG for pretty much all, because it's the best we had.
Basically, we're using RAG and then we say, well, it's hallucinating. And now this is saying,
Yeah.
well, if you're doing long form,
Yeah.
think of an alternative.
Yeah. See, Satyam, so let me ask this question. What is so insightful about this paper? Like, this paper will get published, I'm pretty sure, ultimately in some journal. What is insight? I mean, these are pretty good guys. These are Meta and Carnegie, CMU, and so forth, C Labs. These are big guys. What is insightful is, see, the idea first is the key observation that you tend to have less hallucination when your question is very pointed. But how do you ask a pointed question when you're asking a LLM to describe the entire, let us say,
Solar system.
solar system, or that inherently needs long form, essay form answer, because it's not pointed, number one. The second thing is that what is your clue dynamically, programmatically? How do you know that you may be hallucinating, right? And what this paper really says is that, see, let's use the interplay of two things. We will use something that may be a clue. It is never too sure, but we notice that empirically when things hallucinate, precursor to that are a few low probability tokens. Now, see, that observation could have been made by anyone, right? Anyone could have done that. Actually, you and I sitting with our little LLMs could have done that. These people observe that, and I think some other people may have observed similar things, but that is one crucial. But what do you do about it then, right? So people before then, the prior work has actually tried to do something with it. What they did is that they fed in everything that has been generated before as the search query, right? All the
That
tokens.
search query also wasn't good.
Yeah, so that search query also wasn't good. And what turned out to be good is the specific approach these guys took, for which there is clear evidence that it beats the state, beats all of those approaches.
Right.
That is what is original about this paper. Right? And see, always look at these things in a broader picture, guys. What are things coming from? This is a paper. What are things coming from? Why do LLMs hallucinate? What really is going on? If you have a handle on the theoretical stuff, the math behind it, it is plain as day. But could I have thought of this myself? I may make excuses, I'm too busy, but fact of life is I probably couldn't have. These guys did. The interesting thing about this field is once things happen, it looks
like common sense then.
in hindsight. Yeah. In 2020 hindsight is like, what? Of course. All right. But the thing is that RAG has been there now for more than 2 years.
And now
this has come. Right. In between, there have been approaches that have sort of made small improvement, but this is a significant improvement. Right? So this is what it is. So let's look at that. Yeah, this limiting, however, is in more general scenarios involving generation of long text, where continuously gathering information throughout the generation process is essential. If I ask you to write a thesis, now you better start searching the web, right? Kind of thing. By the way, that thing is called open domain summarization. There's a term I want to introduce because this paper uses. It is open domain summarization. Open. It was used in this paper. What does it mean? Anyone? What is open domain summarization?
Where there's not a lot of information, or it's an open-ended question.
Where it's an open-ended question and not a lot of information. What else?
Like an open book exam.
Like an open book exam, Chandra says. Close. What is open book on the web? Because so far those LLMs don't have hands. So what's an open book exam?
You have information all you want, and I'm asking you to summarize.
That is yeah.
All day.
Yeah. So Chandra hit pretty close to the mark. Basically, open here just means that open web search. You're allowed to do open web search on that topic, gather all the information that you get, and then apply the LLM to summarize. Right. So obviously you could do it with LangChain and so forth. So some of you who are using the agent in LangChain, you remember in NLP we did that. Right. We did the open domain summarization as one of the exercises. So that's that. So this term does come up in this paper. So I thought I'll remind you what it means. So there have been some past efforts to retrieve information multiple times while generating output. So you go on retrieving information. So one extreme case is every sentence that this LLM produces, you search for that, right? You get the search results, feed it in, and now that becomes part of your prompt instruction. What it has generated becomes part of your instruction, and your question becomes part of your instruction, right? What they have found is that, by the way, that for AI might make sense. For any engineer, systems engineer, that would be a blessing or a nightmare. Think of the performance impact of that, right? Every sentence you're using a whole system to generate the next sentence at that moment, right? You're searching, you're doing this, you're doing that. A lot of things are happening. It's a very tedious and expensive process. It turns out that you don't need to do that. And there is a point of diminishing returns. You don't get much, right? So the other limit is, of course, just plain RAG. You retrieve information once and then you produce things from that. There have been some past efforts to retrieve, okay, blah, blah, blah. In this work, we provide a generalized view of active retrieval, augmented generation. Means the LLM is itself actively participating in that, helping you do that. And by giving you the probabilities that you use and you do that, we propose forward-looking active retrieval, augmented generation, FLAIR, right? So, by the way, the word FLAIR, there are other algorithms in AI space with the word FLAIR. So if you Google FLAIR, something else comes up. Huh? But remember that they seem to have also used the same word. What part is forward-looking? Means whatever the next sentence that is generated, don't just let it go out, hide it behind the curtain. Make a decision. Do you want it to go out or not? Right? Or you want to throw it away and just use it for something else? Right? That's the part. A generic retrieval, and they say it's pretty generic, means you can apply to a whole class of problems. Right? Uses a prediction of the upcoming sentence to anticipate future content, which is then utilized as a query to retrieve relevant documents to regenerate the sentence if it contains low confidence tokens. By now, I hope after all the explanation, this should look obvious. We test FLAIR along with baselines comprehensively over 4 long form knowledge base intensive generation tasks data sets. FLAIR achieves superior or competitive performance on all tasks, demonstrating the effectiveness of our approach. Right? So obviously, this paper wouldn't be worth it. These days, it's a sine qua non that you have to beat the state of the art. So we move forward from that. I will leave this introduction because it's about the background and what others have done. For basically what it says is for simple things, it works. I will get to this diagram a little bit later. Let's go straight to the, so you know what retrieval augment. So this is a bit of terminology, setting it up. Can I skip the intro part, guys, which is about background and what others have done and so on and so forth, right? So what we will do is we'll start with the notation. D is the corpus, right? D is the corpus. What is the corpus? What does that scripted D, calligraphic D stand for? It's the set of all documents, right? And remember, guys, here the meaning of documents is different from your meaning of documents. Right? What have you indexed? In your project, you have indexed chunks. So what are your documents? Chunks. The little di are the chunks, right? Here, Wikipedia, the goal of retrieval augmented is to generate the answer. Y is made up of these sentences, S1, S2, M sentences, of which is the same as N tokens. How can it be? Because N tokens are partitioned into M sentences, right? Containing M sentences and leveraging information from the corpus. In retrieval augmented LM, the LM typically pairs with a retriever that can retrieve a list of documents. This is the RQ is the search result, right? For a query queue. So if given a query queue, you get the retrieved results, namely the search results, and you use that, right? Since we focus on examining various methods for determining when and what to retrieve, we follow existing methods, blah, blah, blah. So guys, I hope this is obvious that the large language model takes as input those search results and the input, isn't it? It's written like that. It works on the tuple. It works on this there. More common sense, a very prosaic way of saying is, how is it? Just write it down. 1 document, 2 document, 3 document. Literally write the text down, right? And then follow it with X, namely the question, Q, the question, right? Now let the language model act on it. So it's a one shot. It's just forward pass, right? Here it is. And now I'll sit back, relax, and wait for the text being generated, right? I will say generate 1,000 tokens, right? Or 4,000, at least 4,000 tokens, or something like that, or generate. And it will go on generating till LLM comes to the conclusion that it's done. So now when I put it like this, obviously it looks not so good, right? So that was your single time augmented model. So what are they saying? They are saying that let us say that up to this sentence, Y, T, all the prior sentences using the same mechanism, they have been accepted, right? Now that is your query. What you do is you have to formulate a query. What you do is you take X, let's formulate it. Let me read it out because this is worth reading. To aid long form generation with retrieval, we provide active retrieval augmented generation. It is a generic framework that actively decides when and what to retrieve through the generation process, resulting in an, and this word is sentence is important, resulting in an interleaving of retrieval and generation. Right? Remember, we had two ways of getting answers from the search and from the LM, language model. And you're interleaving, right? Sometimes you're throwing away what the LM produced and say, no, let's go and get some more facts and do in context learning, literally do like sort of educate the LLM a little bit more and then see, does it produce an answer it has more confidence in, right? And you keep doing this, interleaving these two approaches. Formally at step T, greater than 1, assuming that the first time do you have a choice? You just ask it to produce something, right? The retrieval query QT is formulated both on the user input X and the previously generated output so far, right? So what is it that you query for? What you have produced so far and the X. It makes sense that the entire thing you can give. Now you say that, well, isn't it a lot of text to give to search engine? What happens when in Google you start writing a Ramayana?
Lost in the middle.
Yeah, Google produces all sorts of results. I mean, Google actually does a pretty good job because it's very AI driven. With Elasticsearch, OpenSearch, what happens? It will produce lots of irrelevant results, isn't it? Keyword search engines. But why would we? So why is this a good idea? So explain to me, guys, why did these authors believe that this looks like a good idea? Why would you say that this is not a harebrained thought? You don't want to search with huge text if you go into that. Well, multiple reasons. First is that, see, especially if you're doing AI search, the more context you give, the more richer the semantic of your query, isn't it? And actually, you'll get better answers. The whole power of semantic search is the bigger the input, the better, usually better the output. So long as the input is all about the same topic, right?
But you just said that there's a paper which is lost in the middle.
No, that is on the context. That's on a different. That is for the LLM, not for the search.
Okay.
Remember, there are two different words. AI search loves long text, so long as it's about the same topic, because the context, the sort of semantics become clearer and clearer.
Okay, the search
It's different.
is happy when you have more text. But,
That's right. AI search.
But LLM in
LLM
generative form is.
Yeah, that's it. Okay, guys.
You don't want to put in too much context in the LLM because then it's like lost in the middle.
Yeah. When you put too much context, it's lost. Okay. So here it's a good idea because, well, again, as I said, search doesn't mind. The better, the more, the better. Where query is the query formulation function. At the start of the generation, the previous generation is empty. There's nothing. So what do you search for? You search for the user's query, right? Whatever comes, you put it in the thing, user's query, and you ask the LLM to go at it, right? Given the retrieved document DQ, so it will return the documents DQ, LLM continually generates the answer until the next retrieval is triggered or it reaches the end. So suppose somewhere along the next sentence, the LLM comes out with this saying that, okay, I'm done. You're done, right? But barring that exit terminal condition, all you need to know is, do I take it or not? So LLM will base it on its answer on these things. Where does DQ come from? From search. From search, right? Where YT represents the generated tokens and blah, blah, blah. The user input X and the previously generated. At each step, we discard previously retrieved documents. Of course, you don't want to keep on the documents that came long ago and only use the retrieved documents from the current step. So by the way, this is a clarifying point because somebody may ask, oh, by the way, are you using only the documents from the current search or are you also using all the previously retrieved information? That could have been relevant. So they are saying, no, we only use the documents on the current search. Right? Now, why is that a good idea? The previous documents from the previous part also are relevant. I think biryani is having its effect.
Yeah.
So,
He just had biryani.
hmm?
He just came, he didn't have biryani.
Okay. So why would you not do that? The reason is because you're already feeding it when you query, you're feeding it all the output, which was conditioned on the previous documents anyway. And in some sense, the coloration from the previous documents is already well there, right? And so you do that. It would be redundant to pass it again.
So I still have, sorry to ask you a question, but see, let's say the previous search has resulted lots of document, right? And that
Oh,
document.
by the way, you don't, when you think in this RAG, right, please try not to think lots. Don't think hundreds,
Yeah, maybe let's say start with 20 results.
20 results.
Now, who will determine that these document one and query one is going to yield another 10 result, and are they out of this flare?
No, that is exactly the point. No, this is the method. What it says is that, so let's start from the beginning. All you have is the user's query. Describe to me the ancient, let's say, the Harappa Valley, the Indus Valley civilization, right? So
It generated 20.
that is your query. It generated, it will say, Indus Valley civilization is known to have existed between blah blah BC to blah blah BC. But somewhere along that, you just check this one sentence, you check, let's say that this is already 64 tokens. It is not, but let's say, right? You look at this and you ask, okay, is the probability, is the token, any one of their token softmax probability below a threshold?
I see.
If it is not, okay, one sentence, good sentence, right?
Right.
Then you say, okay, continue, right? It starts producing this and it says, right, it was located in ancient, it was located somewhere between, in one of the Greek islands in the Mediterranean Sea, right? And then you notice that the probability looks rather low. So what do? You say, oh, I'm not going to print this sentence. I'm not going to emit this sentence. So now what happens? What is your query? We will talk about the query in a moment, but because that's where the whole technology comes in, right? But your query, describe the civilization, is still there, right? What we will do is we'll do something interesting about this wrong sentence or potentially wrong sentence. They use some clever magic to it, which we'll talk about, to go and search. Okay, go ahead.
Follow-up question, sorry. So let's say it is still behind the curtain. It is not produced and dumped into the
Yes.
prompt.
No, the first sentence which it was confident on, it dumped to the
generates it.
yeah. But it's only when it is not sure. So it is like a layer. It's a decorator pattern, right? If you think about it this way in programming, right? It intercepts what the LLM produces and decides, should I let it be the output or should I go back and re-instruct the LLM?
I thought like it is still like it has collected all the high probability output and then try to figure it out more.
No, it's that is why it's an active process. That's why they use the word active.
Okay.
Right?
It's like a
Forward-looking,
It's
active.
like a streaming
It's a
service.
stream,
You
kind
like
of.
the probability, you let it go. You don't like it, you stop it.
And you
and
do
you
something. Yeah,
just breathe in
exactly.
and stream.
So that's why the word forward-looking. Why forward-looking?
So
Because the
chances of
output
first statement can have a lower probability than the middle of some statement.
No, the minute you have lower probability, you go into the big setting.
No, even though let's the output which you have generated, there has to be some cutoff probability.
No. Let's take a cutoff probability 0.2.
I see.
I'll just take 0.2. Right. 0.2 is actually pretty harsh, but okay, let's take 0.2. So what happens is that, 1 second, I'll come to it. Let's say that the first sentence went through.
And
It's forgotten. You just remember the tokens. Why one? You remember, it's part of your history. That is committed, right? Think of your database language. It's a commit point, checkpoint. It's committed, right? Now the question is, I'm looking at the next sentence. Either everything is fine, I let that also go through, or I say no. So now is the question. I need to, what do I need to do? I looked at the output of the LLM, but I'm the interceptor. I did not let it go out. I am going to now dip into the search engine, get some documents, use that, use the original query, right? And use the tokens that I've generated so far, namely the first sentence, and give all of them, right? Because those are the things I'm sure of. I am taking it as a gospel truth, the documents that are there in my corpus. I'm taking your question as valid. And whatever the LLM has produced with high confidence, I'm taking also as truth. And I'm saying these are facts. What now? Right? So that is what is going on. Now it still leaves the question, one second, Amrit, it still leaves the question, how did I search? I said, I will use the last sentence, the defective sentence or the suspicious sentence, right? And potentially the things, the tokens that have been produced so far and some things as material and it itself to go to the search engine. But how do we do that? Here are multiple approaches they talk about and we'll go over them. So I'll come to you. First you there.
I think that's the question I had, that when you say that I'll let the first sentence go and start the second sentence and deep into this again, what are you looking for? What information you are sending to retrieve again?
No, we'll come to those details. I mean, we are starting on the paper. See, guys, here's one thing about research papers. It is called the IMCR, right? Introduction, method, results, right? Conclusion. And then, of course, the references, right? Oh, sorry, not IMCR, IMRC. Introduction, method, results, conclusion, right? So at this moment, they're just beginning to describe the method. Introduction is over, right? Introduction was section number 1. That is why in most papers, you notice that it literally spells it out. You see, 1, introduction, right? Good papers are all written like this. 2, if introduction is over, what will 2 be? Method. So if you want to save time, jump to method first. Read the abstract, jump to method. Right? 1 second, guys. I'll come to you in a moment. And then will come what? After method comes what? Results, empirical results. Did it work? Prove that it works. Let's go to section 3. Yeah, no, here they're still actually going through the details of it. So it would be section 4 perhaps, implementation details. And then 4 is still implementation details. And 5 is again the methods. And then will come results. 6 becomes results. So from that you conclude that 2, 3, 4, 5, they have a lot to say. They have done a lot, right? Experimental results. And experimental results, right, will obviously, experimental results will always be one thing for sure, right? In the majority of the cases, they would have done some really good work, right? Do you notice that all the green bars are doing better? Green bars are the forward-looking, the flare method, right? And then there would be one good thing that good papers have is something called the ablation studies. So you took this approach. This approach had multiple parts. You used trick 1 or technique 1, technique 2, technique 3, technique 4, right? So now you need to give, in some sense, a weightage. How much did technique 1 contribute? How much technique 2 contributed, and so forth, right? Think of it in some sense as Shapley values, right? Contributory factors. How much did each of them contribute? Doing that is ablation study. Good papers always have ablation study. They will show that if I turn this part off, then this is the degradation of performance. If I turn that part off, because suppose there is a technique you love very much, but when you do ablation study, it turns out that results stay still strong. What does that mean? You may love it as much as you want, it is doing nothing. So ablation studies are important. And then finally, conclusion. There we go, conclusion. And another thing good papers have. See, good papers always not only show their positive results, they have limitations, right? And one of the criteria of research papers to be accepted is, which reviewers consider, is does it show the way forward? Usually in the limitation section, you not only say, oh, this thing it cannot do, but you also open the door for other researchers to continue your work. Are we together? It's very important. Research papers that suppose you say that, I did such a fundamental work on this topic that nothing remains to be done. Right? Actually, yeah, said the last word on the topic. That may be lovely in history or some other thing, sociology or God knows what else. But in research, in STEM fields, it's never the same because knowledge inherently is incomplete. Right? In fact, there's a I don't know if one can directly relate, but there is such a thing as a Gödel's incompleteness theorem that says that scientific knowledge by its very definition will forever remain incomplete. Right? So that's important. So anyway, going back to it, I wanted to finish by now, but I'll just take another 10 minutes. And I'll just show you the gist of the technique, guys. So now, forward-looking active retrieval, what it does is, it basically looks for, I mean, you can now read this paper, it will make a lot of sense to you. So the techniques they use is direct flare. What they found is, since we cannot fine-tune black box LLMs, right? Okay, so let me actually backtrack a little bit. We found, this part is interesting. Yeah. We found that LMs can effectively combine two skills and generate meaningful search queries. What are the two skills? An instruction to guide LMs to generate search queries. See, one of the questions is, suppose the LM comes to the conclusion that I'm producing a token and I don't have confidence in it. The sentence is not. You still have a task. You need two tasks. You need to generate a search query, full search query, that you will feed into the search engine, right? But you can use the LLM itself to create a smart search query, right? So that is one skill that it must have. The second is an instruction to guide LLMs to perform a specific downstream task, namely question answer, whatever it is that you were trying to do, like to create the instruction, right? An instruction to guide LLMs to combine skill 1 and skill 2, and that is this. So basically, it's somewhat self-referential. You can use, one second, guys, I know there are a lot of questions. You can use another LLM to generate all of this, or better still, you can use the same LLM to guide itself, right? It gives meaning to coloration to the word active, right? Okay, guys. So for paucity of time, just give me a little bit of so there's some technical details here. Okay, I'll let you get to that. One of the things they found is, what are the two ways that you can use, what queries that you produce? There are two ways of doing the query. Suppose you have a last sentence, right? And some tokens in it were low probability. What you do is you make it a masked language model of sorts. You mask it. And you give it to that LM, the language model, and you say, hey, here is what we know. Right? What would be a good question? What would be the question that would help fill in these blanks? Are we together? So let us say that it came to the conclusion that the capital of Bihar is Paris, right? And so you masked Paris, right? And then you say, these are the facts, whatever you produced so far. What would be the question to ask in order to complete this sentence? This, put the mask there, fill the mask. And that becomes your one very direct way of questioning it, right? And then there is another technique similar. So I think because there are so many questions and we have 9 minutes left, I will let you guys read the paper. But guys, did you get the main idea of the paper? Right? Read through this. Now you can figure the head out. Okay, questions. First, there was a question in the back. Who was it? Way back there, last one. Oh, yeah. Albert, you had a question, and then I think Amrit, you had a question.
I had the same question.
Okay, Albert.
So this confidence level, what is the confidence out? Is that the probability of the answer?
Just the probability. And go ahead, Patrick.
As it, for the implementation of the masked language model, is this going to be a separate API call that says you are to
Generate a question.
Give
Generate a
this, give, so we have to extract first the uncertain sentence, right? And
Yes.
We're gonna say, given this uncertain sentence,
Yeah,
mask the.
Yeah.
Yeah, mask the specific.
that is right.
and then,
Right.
continue.
So Patrick, what happens is that, see, this is like in programming, you do exception handling, right? Try catch blocks, right? Or try except blocks in Python. It's literally like that. What happens is, if you remember in programming, the moment you go into exception handling, performance is always slower. Isn't it? Because the compiler will always optimize your main code at the expense of your exception handling code. Exception handling code will be thrown all over the place. Same similar thing. As it is generating, if it is generating good confident sentences, all is well with the world. The moment it generates something that is it's not confident on, it's almost like an exception being raised. Then you bring in a technique to handle that exception. So another way of looking at this entire paper from a programmatic way of doing it is you detect an exception and then you handle it, right? You have essentially put your generation in a nice try catch block from a programmer's perspective, isn't it? To get better yield. That's what this paper is. Okay, guys.
So one last question. When you find tokens with low probability, you are essentially making two ways. One is to actually figure out what the question should be and what is the answer to the question also. So in your case, what is the capital?
No. So it's a two-step process.
Right.
First, you generate the perfect question
Right.
From the
That is
LLM.
one API.
from the LLM.
And then the second one is to do the search again.
The search with that. You go and search with that.
Search.
You get the search results. You now create yet another instruction. Forget your previous instruction. You put that knowledge, your generated text, and finally your question. Usually prepending helps. So one of the questions we ask is what order? Prepend everything before your question.
So, and before that, there is a RAG step.
Yeah. So in other words, first narrate the entire Ramayana and then ask Sita kiska baap tha. So it's sort of like that. Patrick, it is like there's a whole story in which there is a king and a queen, they're gods, right? And there's war and many things happen. It's very much like the Greek mythology. But at the end of it, the queen, the joke in India is if you don't get that story right, then you are still asking, who was she the father of? So sort of like that. Yeah. So anyway, that is it, guys. Another 3-4 minutes left. Anybody else has a question? Any comments, guys, for those of you who are remote? Is this paper clear? No. Obviously, we didn't get time to go over every
From the
detail.
implementation. Right now, the paper is clear, but we have not seen the implementation. That how challenging.
So the flow goes as if rank to get context. Context comes into LLM. LLM starts to stop when it gets an uncertain sentence. Sentence gets pulled aside, and then we do a second call that says, given this uncertain sentence, mask and technical.
Yeah.
Mask and then
What's a
the
good
best-
question
what's
to
a good
have?
question?
And then
the
go to
third-
search.
And then go to search, and then third call. Given
Continue
that-
now. Continue now with this information.
And that's all on the stack. So you have to go back into the previous call.
Yes.
So given that our previous one is RAG, is this the next project?
This is your next one. Try to
Well,
observe.
RAG on steroid.
This is, I mean, unless you don't have RAG, how do you do it?
So guys, it's worth it if you can do this and look at the GitHub. They have a GitHub and all of that. You can do that. Sometimes you learn a lot by reading the code. Yeah. And there are websites like code with annotated papers, right? Paper with code, explain. I mean, paper explained with code. What's that? Yeah. Right. So there are many such resources. Actually, Patrick, you have a lot of these good resources. Send them to me. I'll add it to the course portal. So use that, guys. Read this paper carefully, please. and go to the GitHub, look at the models, and better still, if you have this stamina, see guys, create an implementation, a basic implementation like this on your own. Try to do it. Don't have to do a full-blown one, like a complete state of the art, but try to. It's not a lot of, I hope it's not. See, getting these ideas is hard, right? In hindsight, they look obvious. But once you get it, you realize that you can do it.
Also, typically, is it better to use just a low parameter model or like an older model that's not very smart?
No, in our case, see, we are bound by realities. All of us are sitting on 4090s. Right? So whatever fits into 4090.
But like GPT-2 versus Mistral 7 will.
Oh, I would any day prefer a Mistral 7.
Mistral, so it's still a smart model.
Smarter model.
Also, we are switching to Mistral now.
Okay, guys. So remember, half an hour break and the next paper. It's totally up to you. Remember, these paper readings are sort of optional here onwards, and your projects, which we will start evaluating at 5:30, is also optional. So if you guys want to dedicate your focus to coding, please continue to make progress on your project. By the way, how many of you found it useful? All right, so we'll do Video Llama, half an hour sharp.